In the previous experiment of baggy science, you would have noticed that during the reaction, the sandwich bag increased in size, which to some may suggest an increase in mass. However, upon comparing the initial and final mass of the bag, they should be pretty much the same. Now, this reflects the law of conservation of mass, which states no matter what's created or destroyed in the process as the reaction vessel, as in the bag, was closed. Therefore, the mass of the reactant should equal the mass of the products. All chemical reactions require balancing, as this addresses the conservation of mass. The number in front of each species refers to the quantity of the molecule and is known as a coefficient. For example, in the case of the synthesis of water, you would require 2 parts hydrogen gas and 1 part oxygen gas to produce 2 parts water. Now, these parts can be in terms of, say, mass, like grams, or in terms of molecules. Now, these quantities are important to know to minimize wasted reactants or calculate expected product quantities. Think of a cheese toastie. A good one requires 2 slices of buttered bread and 2 slices of cheese to produce the toastie. If you're given 2 slices of buttered bread and 3 slices of cheese, you would only end up with still 1 cheese toastie. The 1 slice of cheese would be a wasted reactant in the process. The study of these quantitative aspects of formula and equations is known as stoichiometry. Because the mass of the atoms are so small, they use relative masses when compared to carbon, which was designated an atomic mass of 12, because of the 6 protons and 6 neutrons within the nucleus. Because hydrogen is only composed of a proton and an electron, it's 1/12 the mass of a carbon, so is designated an atomic mass of 1. All other elements are compared the same way. However, the discovery of isotopes complicated this method. Therefore, relative atomic mass should be considered the average relative atomic mass of the naturally occurring element. It used to be called atomic weight, but that all changed. As molecules, the relative atomic mass can still be calculated by adding all the masses as described by the molecular formula. For example, water, which is composed of 2 hydrogen atoms and 1 oxygen atom, has a relative atomic mass of 18.02 to 4 sig fig as it's given in your periodic table. Notice how there's no units because it's relative to the mass of carbon-12. Now you're probably wondering what happens if you need to calculate the relative atomic mass for metals or ionic compounds. Because the formulas only represent simple whole ratios and not standalone molecules. It's pretty simple. Just do the same thing, but it's called relative formula mass. For example, sodium chloride. Add the mass in the correct ratio and bam!